Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we begin a new chapter in the Big Ideas Math Integrated Math 2 textbook on Chapter 5 regarding probability. Oftentimes, I'll probably just call this statistics, the stats chapter, because there's classes with stats, and this is where we generally dive into probability, or algebra and geometry classes, and in this case, integrated math too. And this is something that I'm excited to go over. I do like the kind of real-life application these kinds of problems have. You're going to see a lot of problems regarding rolling a die, flipping a coin, or drawing a card, or taking marbles out of a jar, because those are just commonplace things where we know what kinds of outcomes we can have on them. And so it's just a good way of talking about probability, especially when it comes to the gambling scene. So anyway, with that, without further ado, we're going to look at section 5.1 on, I think it's called sample spaces and probability, something like that. I know sample spaces are definitely a part of it. And I just know that it's a good intro into what we do after in a formula basis. Some of these things will have formulas, but to make sense of what those formulas are and why we dig things out the way they do, I think this one has great conversational pieces to it, at least just by the title and what I expect to get out of this. So if you want to see more with this, please jump to the description section down below and you can download the PDF there and follow any other videos in the IM2 playlist you can find down below as well. If you want to continue with this video, I'm going to start with the lecture portion. If you want to jump to the solution guide portion of the problem set, you can find that in the timestamp. I think someone just hit a home run. I'm seeing in my blurred vision a fence and someone's rounding the bases. I think it's a Brave. I don't want to look. I want to start with you guys. Without further ado, let's go ahead and get started. Go Braves. What you will learn to find sample spaces and theoretical and experimental probabilities and also odds. Probabilities and odds are close to the same thing, not quite. We'll see the difference, I'm sure. They'll talk about them. I believe it is called sample spaces and probabilities, just based off what they say, what we're going to find. And a lot of different vocab. I'm not going to read the words now, but you can see them. I already said a few of them. It looks like a lot of them pop up on the first 4 pages within the lecture, of course. And we need to know about tree diagrams. Oh, I know why. Okay, so yeah, there's a great breakdown. In fact, I think I'm looking at one right now. Pretty much a tree diagram there. So we need to know what tree diagrams are, or at least when we visualize them. Okay, sample spaces. A probability experiment is an action or trial that has varying results. Okay. The possible results of a probability experiment are outcomes. For instance, when you roll a 6-sided die, there are 6 possible outcomes, 1, 2, 3, 4, 5, and 6. So those are the possible things that can show up in your outcome set. They don't always, but they can. A collection of one or more outcomes is an event, such as rolling an odd number. Yeah, I'm going to be saying that word event quite often. Rolling a die, flipping a coin, drawing a card, picking a marble out of a jar. That is a single event, and you can have multiple events occur. If I flip a coin and then another coin and third coin, things like that. Those are different events in a trial, in an experiment. The set of all possible outcomes is called a sample space. So that's a lot of vocab within there, and I'm going to try and say those phrases as often as possible. I don't know how often I'm going to say this one, but you'll hear me say these other phrases, sample space, event, and outcome, throughout the chapter, really. I think that's why it's just a nice breakdown of saying, hey, let's tell you about them right now from the jump. So finding a sample space, you flip a coin and roll a 6-sided die. How many possible outcomes are there in the sample space? List the possible outcomes. So the sample space here is saying, well, if I flip a coin, I can land on either heads or tails. I can roll a die. I can either get 1, 2, 3, 4, 5, and 6. But because you're going to do both, they want to know what different things are possible. And what's possible is if you flip a head and then roll 1, 2, 3, 4, 5, or 6, that's 6 different possible outcomes we're talking about. Heads and then a 1, heads and then a 2, etc., all the way up to 6. Or I could have flipped and landed on tails to begin with and then rolled 1 through 6. And that's 6 different outcomes. Sure, it's tails the same time each time, but it's a specific outcome that you have. It's like a lottery ticket thing. You know, it's like you got to get this number and then this number on top of it, and they are 12 unique different sets. So the way that they abbreviated it is right here. I'm sure because this is an example, we're going to have to do the same thing. So you're going to see me abbreviate in that same vein, I suppose. H1 for heads 1, T6 for tails, and 6. So there are 12 possible outcomes. 12 possible outcomes. There's a monitoring progress, seeing different ways you flip 2 coins. We'll just say those out loud. You can have heads, 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 tails, tails, heads, or tails, tails. That's 4 different possible outcomes. And another one, we'll leave it. The theoretical probabilities. Okay, because there was theoretical and there's experimental. Let's see about theoretical. The probability of an event is a measure of the likelihood or chance that the event will occur. Probability is a number from 0 to 1, including 0 and 1, and can be expressed as a decimal, fraction, or percent. So it's great that they're showing all three different things, and I want to talk about that as well. When you have, 1 out of 2 probability of doing something, that's literally 1 divided by 2, like 1/2. And you go to the calculator, it's going to say 0.5, this number right here, right? So, but we know that 1 out of 2 is 50%. You get 1 out of 2 on a quiz, you got 50% on the quiz, 1/2 chance is 50% chance. But the number that is calculated is the 0.5. And I'm not going to get deep into the whole converting decimal to percentage, although you shift it 2 to the right, multiply by 100. But often we see the numbers like this. And there are some books that don't even bother with the percentage version of the answer. When they say the probability is 0.62, they'll just say that without even saying 62%. They just mean 62 out of 100, like whatever it is. So, just kind of keep that in mind when we have that. We can leave all answers as fractions or decimals or percentages or do all three, right? It depends on what you're talking about and what they ask for specifically. I'll probably look at the examples that they say and follow suit with that. If they do all three, I guess I'll have to do all three. What I also like here is just that understanding of what we have from 0 to 1 or 0% to 100%. We know 100% means there's an absolute certainty of something happening. 0% is an absolute impossibility. And those numbers reflect that, 0 and 1. You can't have more than 100% probability of something. You can't have less than 0% of probability of something. So it's got to be between those two. And then they talk about how the likelihood, how we interpret something. When you have 75% odds of something that's considered likely to happen, because it's more likely than not. It's more than 50%, and you're teetering toward certainty. You're halfway between equally likely and certainty. And likewise, unlikely is 25%. I mean, that's just kind of a middle road thing. If I say 30%, that's also very little likely. Things like that. Anyway, what did that have to do with theoretical probability? There's something specific. All right, here it is. They go further. The outcomes for a specified event are called favorable outcomes. I often don't say the phrase, it's not their fault, their phrase is fine. It's just if I say desired outcomes, I mean the same thing. So I don't know if they're ever going to say the phrase desired outcomes. If I say it, I want to make sure you know what I mean. When all outcomes are equally likely, the theoretical probability of the event can be found using the following. The theoretical probability of something is the number of favorable outcomes divided by the total number of outcomes. So they're going to show some examples, but the idea of theoretical probability is, in theory, what would we expect to occur based on the randomness and equal likelihood of something happening. I know we've run across problems in this book, or at least you will at some point, where it says, you throw a dart on a dartboard. Each part of the dartboard is equally likely to be hit. So theoretically, there are some probabilities to land in this zone, etc., as far as the area that it covers, because it's just equal likelihood of happening, and we can calculate that way. And so what I want to say about the desired or favorable outcomes is that favorable doesn't necessarily mean that it's good. I just want to make sure that you know that, right? If I land on heads, that doesn't necessarily mean it's good, but if they ask what's the probability of landing on heads, heads is the one that I'm seeking. Probably more sought outcomes is the better phrasing, but favorable is the way that they're saying the phrase. Desired is what I say. Okay, the probability of event A is written as P of A. So the probability of event A occurring. So they're going to show you some notation with this. We want to see what it looks like. That A is the favorable outcome in this case when they ask. Let's see. Okay, example 2. Finding a theoretical probability. A student taking a quiz randomly guesses the answers to 4 true-false questions. What's the probability of the student guessing exactly 2 correct answers? Good kind of question for students to observe this kind of thing. And I'd have a lot more to say on this if I shouldn't digress. But I have anytime that we have a test, most often a final, and we say it's multiple choice, students often go yes. And I kind of say, wait a minute, on several things. Their thing is, well, 1, I know that the answer is one of the 4 options, and 2, I can guess randomly and possibly get it right. And you're right, but there are also answers on there that are meant to run you astray. Like you might land on a wrong answer because we anticipated that you get it. These things are all or nothing. You have a 25% likelihood of getting something right, which, as you just saw, meant unlikely. And wow, the odds of getting, if you randomly guessed, I literally let a calculator, a computer randomly guess for you. You know what I mean? So it's not driven by, I got to always hit C at some point and I can't have 5 A's in a row. But even if you did that, the likelihood of even getting like 35% or more turns into like 0.001. It's really low. It's really low. Anyway, yeah, don't ever expect to pass something by randomly guessing. You know, obviously, if you do process elimination, get some other things right. And knock on wood. Anyway, what's the probability of a student guessing exactly 2 correct answers? Now, it's not 50%. It's not 50%. So, first of all, what we have to understand for this problem is 4 true-false questions. True-false means there's equal likelihood. Well, I guess we're not talking about probability yet, but there are only 2 different kinds of things that you can get. Either get something true or get something false. Now, because you have 4 questions, there are different ways that you can arrange how many you get correct and incorrect based off that. I should have mentioned true-false. I should have said the correct or incorrect. So find the outcomes in the sample space. Let C represent a correct answer and I represent an incorrect answer. Possible outcomes are this. So it's possible that you can get none of the questions correct, in which case what happens as the outcomes in the sample space, we see it as I, incorrect. You can get 1 correct. You can either just get the first question correct, or just the second, or just the third, or just the fourth. I now realize that if we're doing these problems, I'm going to have to write a lot, because if this is another kind of example, we're going to have to do a lot of this stuff. So this might take a while. The lecture itself is already past the 10 minutes, so this will take a while. Exactly 2 correct is the one that we're kind of looking for, right? The favorable outcomes, what we're seeking. So you can either get the first 2 incorrect and the next 2 correct, or 1 and then the other like that, the 2 in between, the 2 on the outside, the first and third, or the first 2. Those are all the different ways that you can get 2 questions correct. 6 different ways that it's possible to happen. You get 3 correct like this, and all 4 correct in only 1 way, literally just getting all 4 correct. So when you count this up, there are, and they say the number, there are 16 different ways that you can get questions correct or incorrect on a test. Like, no other person is going to have a different kind of way of getting questions correct or incorrect. And if you guess randomly, we want to find out what the probability is of getting exactly 2 correct. So what we want to do says there are 6 favorable outcomes with exactly 2 correct answers, then total number of outcomes is 16. We're going to divide the 6 different ways that you can get 2 correct by the number of ways you can get any correct, period, or incorrect, or what have you. So they're going to divide 6 by 16, which reduces to 3/8. And you want to ultimately always reduce your fraction as an answer, even if it's out of 100. And it looks like they show it as a percentage as well. So I'm probably going to have to get used to the fact that I'll have to do that division if I don't know what the value is. I did know 3/8 is 37.5%. I didn't know that was the answer until we saw it, but that's the idea. You have a 37.5% chance of getting exactly 2 correct. Now, is that truly desired? I mean, that's only 50%. No, not really. And you have equal likelihood of getting 3 correct as you do getting 1 correct, because that's 4 out of the 16 ways, or 1 out of 16 getting all correct, 1 out of 16 getting none correct there as well. Ultimately, all your different outcomes needs to add to 100% chance of getting any of them correct. In fact, they're saying that right now. The sum of the probabilities of all outcomes in a sample space is 1. Now, so that just means that when you add up all the different ways of probabilities you can get something, what's the probability of getting 0 correct, and 1 correct, and 2 correct, and 3 and 4? You add up all those probabilities, that should add up to 100%. If there's anything left over, or you went over, something went wrong in your math or your setup of something. Now, when you know the probability of event A, you can find the probability of what's called the complement of event A. Complement is spelled the same way that you see with like complementary, supplementary, like angles that add to 90. In this case, this is probabilities that add to 1, and specifically a case where either it does happen or it doesn't happen kind of way. So it says if you know the probability of an event occurring, and I don't know if this is going to be their example, like getting 2 correct, we could find the probability of getting not 2 correct, because we know that that should add to 100% with the 2. So the complement consists of all outcomes that are not in A, and is denoted by, I think that's A bar. Yes, oh, there it is. It's denoted as A bar. I've seen different ways as well, like this, A sub C, the complement of A. I've seen A naught. Is that a negative A? I can't remember. Not A. Anyway, A bar. We're going to try to remember A bar. You can use the following formula to find probability of A bar. It's 1 minus probability of A. So they're going to do some examples, but remember 1 means 100% in decimal form. So you roll 2 6-sided dice, find the probability of each event that the sum is not 6, that's part A, and part B, the sum is less than or equal to 9. Now, you can do this one of two ways. If you want to find that the sum is not 6, you could find every sum that's not 6 and do that. But what you could also do, if it's easier in the case of sum is not 6, is find the probability that the sum is 6 and take that probability away from 100% to figure out everything else. That's the complement. So what they're going to do is do that. Probability that the sum is not 6 equals 1 minus the probability the sum is 6. So there are fewer dice roll pairs that get you a sum of 6 than the sum of not 6. So it's probably easier to do that. What are different ways to get a sum of 6? 1 and 5, 2 and 4, 3 and 3, 2 and 4, 1 and 5. I should have said 5 and 4, 5 and 1, 4 and 2, 3 and 3, 2 and 4, 1 and 5. So there are 5 different ways you can do that. That must mean there are 31 different ways you can get a sum that's not 6. Because this sum is 2, this sum is 8, this sum is 9, this sum is 12, things like that. These are the only ones that have 6. So 5 out of 36 odds to get a sum of 6. Not odds, excuse me, probability. 31 out of 36 probability to get a sum not 6. That's around 86.1%. This time they wrote the decimal. So I don't know whether I'm supposed to write the decimal or percentage suddenly. Probably the sum is less than or equal to 9. Once again, looking through the sample space here, we can kind of count all those different favorable outcomes. So if you want to find less than or equal to 9, what's the opposite of that? Greater than 9, right? The sum is less than or equal to 9. Looks like it's going to be a great set of those. Where is 9 itself? 6 plus 3 is 9. 5 plus 4 is 9. 4 plus 5 is 9. So all of these ones right here are 9 or less. I believe that those should total to 9 or less. Anything else should total to 10, 11, or 12. And if I count those ones up right here, 1, 2, let me use my stylus, 3, 4, 5, 6. There's 6 different ways that you can get more than 9. So if you do 1 minus 6 out of 36, that gives you 30 out of 36. By the way, 1, you get a common denominator, right? 36 out of 36. 36 out of 36. That's what 1 is. And 36 minus 6 is 30. So if there are 36 values total, I guess we didn't talk about that. There are 36 values total in the sample space, and 6 of them get you a sum of 9 or more. You can take those 6 away, and then you get 30 out of 36, which this time reduces to 5 out of 6. That probability is about 83%. 83% chance. Okay, I'll skip by those. Let's talk about experimental probabilities. An experimental probability is based on repeated trials of a probability experiment. So, it's me actually flipping the coin. If I say, what are the odds you land on heads or tails of something, we say 50%, right? One half for both of those. But if I then flipped a coin 50 times, does that mean I will land on it only in heads exactly 25 times? Maybe. It's probably even the most likely. But no, not necessarily. I could land on it 20 times. I could land on it 10 times, all 50 times. Less likely, but I could. And that's the experimental probability, actually doing the trial. Are we going to actually do the trial? No, they'll give us some things, and they say these were the results. But that's what they're talking about, the repeated trials of a probability experiment. The number of trials is that's the difference. Theoretically, you flip a coin, you should be landing on heads 50% of the time. In an experimentation, it's just whatever the trials showed. So there's that. The number of trials is the number of times the probability experiment is performed. Each trial in which a favorable outcome occurs is called a success. So once again, when we talk about favorable outcomes and stuff like that, and a success, if I land on heads, am I successful? I mean, is it a good thing? Not necessarily, as in, if this is success, the other's called failure. What if I wanted tails? Truly, I don't know. But anyway, it's called a success in that case. The experimental probability can be found using the following: number of successes over number of trials. It's still the same thing that we're doing in probability. It's just in experimentation. So here's an example. Each section of the spinner shown has the same area. So there are 4 parts of it, so a quarter each, 25% of the area. So theoretically, you're equally likely to get either of these and 25% at 25% per. But the spinner was spun 20 times. Does that mean they got 5 each? The table shows the results for which color is the experimental probability of stopping on the color the same as the theoretical probability. So we're trying to find which one also would give you 5 out of 20, one fourth chance, 25% chance on this one here. Because each of these, in theory, should give you 25% odds. You spun it 20 times, which one gets you 5 of them? Looks like it's red, actually. Red is 5, here we go, 5 out of 20, which is 1/4. Green was 9 out of 20. That really upset the odds. And then blue and yellow, 3 each. Now, that should add to 20, and it does. But the experimental probability of stopping on red is the same as theoretical probability. Will something always be the same? Well, in the book, probably. In actual trials, no. What if I spun it once? You can only land on one of them, assuming there's no in between. It's not both blue and red. Okay, let's keep going. Solving a real-life problem. I don't know if this is experimental or not, but... in the United States, well, it's a trial. If it's a study, yeah, kind of experimental, if you will. In the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least one pet. The types of pets these adults have are shown in the figure. What is the probability that a pet-owning adult chosen at random has a dog? So this number is everybody's, let's see how I say this. This is the sum that adds to that number there. That's everyone in this survey. I assume. Let's see. I'm trying to add that up and see. Actually, no, that's not necessarily true. This is how many animals that they own in total. Yeah, that doesn't add to 2184. I don't think. Anyway, let's keep going. The number of trials is the number of pet-owning adults, 1,320. Well, that doesn't add to 1,328, but remember, you can own more. They can have more than one animal. So you can have a dog and a cat, or you can have 3 dogs or whatever. And there's just that. Anyway, a success is a pet-owning adult who has a dog. From the graph, there are 916 adults who have a dog. So notice they say, what's the probability a pet-owning adult chosen at random has a dog? They say a pet-owning adult, and they say 1,328 of them have at least one pet. So you're not looking at this number here. You're looking at this number here when it comes to the division. Now, there are 916 dog owners out of the 1,328 pet owners, not 2184. Okay, I guess I don't know if the 2184 actually comes into play. But you're not dividing by 2184. There was a survey of that many people. That's not being used, just the pet owners. The probability of pet owner, and that's around 0.69. So 69% probability that a random person, adult chosen at random, has a dog in this set. Okay, odds. The odds of an event compare the number of favorable and unfavorable outcomes when all outcomes are equally likely. So it's like probability, but you're not dividing by the total. You're dividing by everything that's not what you're talking about. You know, when we say there are 2 to 1 odds on something like that, 2 to 1, we might write it like this as like a ratio, but that also means 2 out of 1, 2 over 1. 2 over 1 is not possible when it comes to probability. That doesn't mean 200%. That means there's likely you have, twice as much chance of making something happen as you do not making something happen, right? Winning or whatever. 2 to 1 odds. You're twice as likely to win than not win. So favorable out of unfavorable, or lose, whatever. There's odds in favor of and odds against. So unfavorable outcomes is the other way when they say odds against. So that word for versus against does matter. And let's hope that they use examples to kind of do those. If not, we're going to do them. Example 6 on finding odds. In example 4, find the odds in favor of stopping on yellow. So I assume they mean the experimental one. So in odds terms, in just the set here, there were 3 spins that were yellow out of 20. But that means that you have 3 to 17 odds of landing on yellow because either it's the 3 of landing on yellow versus... Oh, I'm sorry. I guess it was the theoretical probability. Okay. Anyway, let's say that again. You had 1 in 4 chance probability, 1 in 4 probability of landing on yellow, but because there are 3 other colors, it's dividing yellow by either red, green, or blue, the 3. So 1 to 3 odds. You're 3 times less likely to land on yellow than you are the other colors, is what they mean. Okay, making a decision. The probability of winning a balloon dart game is 0.2. That also means 20%. The odds of winning a ring toss game are 1 to 5. Which game gives you a better chance of winning? Now, you might say, hey, 1 divided by 5 is 0.2, and it is. But because this is odds, 1 to 5, odds of winning a ring toss means you're 5 times less likely to hit a ring of winning a ring toss than you do winning a ring toss. Which means you have 1 in 6 probability of winning that ring toss. That's 1 over 1 plus 5. There are 6 total outcomes here. Well, not outcomes, but as far as the odds go, which is 0.17. And 0.17, 17% is less than 20%. So because 0.2 is greater than 0.17, the balloon dart game gives you a better chance of winning. So that's odds versus probability, and they mixed and matched there. Okay, that was a pretty long lecture as an overall. It was probably my longest I've ever done, and it was probably because I stumbled upon this because I didn't prep it beforehand. I never do. I never will. And if you spent time understanding that, fantastic. Sorry for spending too long on it. But let's get to the vocabulary and core concept check. Describe the difference between theoretical probability and experimental probability. So the way I was kind of saying it was theoretical probability is in theory. Theoretical probability is based on total number of outcomes, while experimental probability is based on number of trials. So that's having favorable outcomes versus total number, and then trials there. So something in theory without experimenting on it versus actually having experimentation on it. Explain how the probability of an event differs from the odds in favor of the event when all outcomes are equally likely. So odds are dividing by the favorable outcomes by not by the total number of outcomes, but by the unfavorable number of outcomes. And that's the difference there. Okay. All right. It seems like I'm going to be talking a lot during this thing, and I am running dry on my water here. So I'm going to go ahead and fill this thing up, but I'm going to jump right back and we're going to start the problem set. Okay, I am all replenished, so I'm going to go ahead and get us started. We are going to get to the problem set. I believe it's numbers 3 through 30 something. I have no idea. Let's go and take a look. Numbers 3 through 32. Okay, in exercises 3 through 6, find the number of possible outcomes in the sample space, then list the possible outcomes. So we're going to list them. I'm thinking about whether we should talk about mathematically how it works, because it does say find the number and then list them. I feel like I want to list them first and then talk about the idea. I thought we were supposed to do that because I feel like everything else was supposed to be formula related after. But here we go. Number 3. You roll a die and flip 3 coins. Okay. Now, when we're talking about the die, we're talking about the possibility of 1 through 6, right? So we can either do a 1, 2, 3, 4, 5, and 6. This isn't me listing them. This is giving you the idea. And then flipping 3 coins, you can do heads or tails. Now, when this occurs, remember there are 3 different coins we're going to be flipping in this case. So when this happens, understand that we have, and I might be typing this next time, but here I can roll a die and land on a 1. And then when I flip 3 coins, right, I can do heads, I can do another heads, and I can do a third heads. That is one of the outcomes. I feel like suddenly I want to type this thing out. So, because this might be a while. So flipping 3 coins would be heads, heads, heads. But that's just one possible outcome. How many more are there? Geez, that's a lot. Because 1 heads, heads, heads. I guess I'll hit the tab button when I do this. I might have to move the 1 through 6. Well, I'll move them up. Sorry about this. I didn't really plan. I didn't plan the stuff. I don't know what it's going to look like ultimately, so I'm trying to think about what to do. So there's one outcome. I don't know if I want commas or tabs or whatever. Then there's 2 and heads, heads, heads. And, basically heads, heads, heads each time. So copy and paste, of course. And then 3 heads, 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 4 and 5 and 6. Those alone, that's 6 different outcomes for just that set with just heads only. Now we do 1, 2, 3, 4, 5, and 6. But let's say instead of heads, 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 you had heads, heads, tails. What if it looked like this instead? And that's just one set with one tails thing involved. What if instead, let me do the heads one. What if instead that last one was still heads, but the second flip was tails? So like this, tails, tails, tails. You know what I almost feel like doing? Well, in some capacity, these are not misspelled. In some capacity, I hope that at some point you understand what I'm doing, that I can pause, get this all done, and then just bring the video back and say, okay, here are them all, which I probably will in just a moment here. Oh, you know what? Let me not do this one just yet because I want to talk about how I'm probably going to arrange them. So give me 1 second. I'm going to bring those back to heads again. Let's do this one instead like this, because I don't just want to do all the ones that are just one set of tails. I think that's harder to do than what I'm going to do here. And I'll kind of explain what I do here as best as I can, because the last set is going to be most important for me to look through. So if you notice so far, we've done everything where heads was the first coin that was flipped. And then what I'm doing is I'm changing that last one afterward. It's kind of like counting up your numbers up through 100 or something like that. I'm going to keep that, or to 200. I'm going to keep the hundreds digit the same while I change all the other ones. So here, I keep heads the same. Actually, here, let's just look down this list. Just ignore the ones. I have heads, 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 and heads, heads, tails. I change that one to tails. And then I bring it back to heads as I move this one up to tails. And then I bring tails back into there. And now what I'm going to do is change the heads, the first heads, to a tails. So it'll be this entire set one more time, only basically doubled. We'll take everything that we've done right now and we'll double it, but I'll change this last set here to tails, the first letter being there. And what I was thinking was maybe I could have ChatGPT help me with just getting these. Hey, could you give me this, but instead of an H here, can you change it all to T? And absolutely it would help me with that, so I don't have to do this. If you have to write this for a problem, oh my goodness, that's a lot. That's a lot for you to do. It's even a lot for me to do this, and I had to copy and paste and just change these here. But wow, it's quite a bit. What a cruel first problem for them to do. I'm very sorry. But hey, this one is going to hit the entire sample space, right? This hits the entire sample space. Notice that 1 through 6 is landed on each time that we consider the different coin flippage. And within that coin flippage, there are 8 different ways that you can arrange that. Because with just the one alone, heads, 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 tails, heads, tails, heads, heads, tails, tails. And then turn the first one to tails, tails, heads, heads, tails, whatever. Like that. And then so ultimately you have 6 times 8, which is 48. And maybe that's where I can just kind of get you that formula there. But 48 total outcomes in the sample space. That's just one problem. I hope they're not all like that. I'll just say 48 outcomes next time. So that's number 3 with that set. Let's go to number 4. This video might be a while. You flip a coin and draw a marble at random from a bag containing 2 purple marbles and 1 white marble. What I want to hit home with this stuff as a whole. Now, flipping the coin is heads or tails. And then from the bag, you have 2 purple and 1 white. Even though these are both purple, just like the heads, well, yeah. Even though they're 2 that are purple, you want to offset the fact that there are different ways that you can get purple ones, if that makes sense. So like this purple is different from that purple when all's told, because the probability will kind of affect the outcomes in the end. So maybe I should call this purple 1 and purple 2 to just really hit home what they're talking about. But the fact of the matter is they're both purple when you account for them. I don't know if I'll call it that because I have to type these out, or I want to type them out. But what you can do is you can land on heads and take out a purple, or let's see, should I say tails next? Or tails and take out, let's see. You can learn, okay, I'm trying to think which way I should do it. Can land on heads and take out the purple, land on heads, take out the other purple, or land on heads and take out that one white. Or you can land on tails, take out, oh, this is a small sample space anyway. Tails take out the purple, tails take out the other purple, or tails take out the white. In that sample space, there are two different outcomes for heads and tails. There are three different outcomes here, even though two are the same color. That is a total of 2 times 3, which is 6 outcomes. And you can see those 6 outcomes that are there. And again, it's just, there are different purples in there. You might say, what does it matter to me? It's all purple. It matters when it comes to probability. It matters when it comes to probability because that's ultimately what you can get with that set, if that makes sense. Okay. Because you're more likely to get a purple than a white. All right, number 5. Number 5, a bag contains 4 red cards numbered 1 through 4, 4 white cards numbered 1 through 4, and 4 black cards numbered 1 through 4. You choose a card at random. So red, I'll use R. White, I'll use W. Black, I'll use B. Black, I'll use B. And then you have the numbers 1 through 4, and they're all labeled that. It says you choose a card at random. I don't know if they're talking about getting a probability for us now, but for the red, you can get 1, 2, 3, or 4. From white, you can get 1, 2, 3, or 4, and black 1, 2, 3, or 4. Now, these are all, see, unlike the other ones, it's not you draw a card and then draw a number. You are drawing a card, and the cards have numbers on them. They have 2 designations to them, a color and a number. In total, they're asking how many different cards are there. You can say 3 by 4, but you're not multiplying those 3 by 4 for that reason anymore. This is just 12 different cards. So 12 outcomes when all is said and done. It is 3 by 4, but not in the same way that the others are 2 different events. Yeah. Okay, number 6. You draw 2 marbles without replacement from a bag containing 3 green marbles and 4 black marbles. So so the phrase without replacement means you don't put it back in. So if I draw a marble, it says 3 green and 4 black. If there are 3 green and 4 black, then there are 7 marbles. If I draw a marble out of there, there are now only 6 marbles left in there. And the different kind of marbles that you have depend on what you chose before. So there are 3 green. I really wish I almost did have G1, G2, and G3. And 4 black. It's just that's going to be hard for me to type out, and I do really want to type these. But just understand the pairing can be this. I can draw this green, and I could draw this black, this black, this black, this black. But guess what? I could also draw this green or this green. If I draw a green, then I would be drawing 2 other sets of greens. Or, I still have 2 other greens to draw from, basically. And that's still what remains. And then I have this green to do the same thing with. I could get this black or this or that, and these 2 greens with it. So there are a lot of different things that you can get there. Keep in mind they're all, it's not greens or blacks. They're all basically a part of the same set. Just clump them all together. So I'll just write that out. Just 3 greens, 3 green, 4 black. So what does that sample space look like? Just imagine that you have, here, let's do them in order. G, 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 B, 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 B. That's not my sample space, by the way. And this one's probably better to count out to make sure you understand what the arrangement actually is and how this one works. So this one here, if I do the first green, what can I choose? I can, because we're choosing 2 marbles. 2 marbles. If I choose this green, I can either choose that green, or with this green, I could choose that green, or with this green, I could choose that black, or this green, I could choose that black, or this green, I could choose that black, or this green, I could choose that black. I've listed out all the different ways that I could choose things from this green starting off. Now let's look at what happens if I chose this green first. Then I could either choose this green, or from this green, I could then choose this green, or from this green, I could choose this black, or this black, or this black, or this black. And it looks like there's going to be no change for the third green set as well, right? If I choose this green, it's either 1, 2 greens here, or the 4 blacks. So it seems no matter which green I choose, I have those things, but I have to arrange for all the different possibilities with that. Now I could choose this black, and with that black I could also choose this green, or with that black I could choose this green, or with that black I could choose this green, or either of those other three blacks. And this is going to repeat itself for this black. It's going to repeat itself. For this black, it's going to repeat itself. And for this black, it's going to repeat itself. So this is the sample space. I don't know if this is the best order to write them or anything like that, but this is based on the arrangement of what we have. Now, how many are there total? It's 7 times 6. So 7 times 6 gives you 42 outcomes. Now, as we're going to dive into formula things in the future, where does the 7 times 6 come from? And assuming I can kind of talk about this part now, you think about how many different ways that you can choose something in the first slot. There are 7 different ways to choose something in the first slot. But because you don't replace the item, how many different ways can you choose things in the second slot? There are 6 of them. And these become multiplication for the arrangements. If you haven't noticed yet, the number of arrangements comes through multiplication. If I could replace it, it would have been 7 times 7 because I could ultimately possibly choose that same exact marble again. I take this green and then I replace it back into the jar and then I have green again to choose from. So that would suddenly be 7 times 7. But in this case, it's 7 for the first set, one of these, and then whatever you choose after that that's gone, there are 6 left to choose from. That's why it's 42. All right, that was pretty long for those first 4, especially since we had to list the things out. Let's see if we have to keep going with that. Number 7 on problem solving. A game show airs on television 5 days per week. Each day, a prize is randomly placed behind one of 2 doors. The contestant wins the prize by selecting the correct door. 50% chance. What is the probability that exactly 2 of the 5 contestants win a prize during a week? So with this one here, we might have to lay them out again to make sense of it because this is one of the ones that you won't have a formula for until later. Maybe 5.4, maybe 5.5. I don't know what section it's going to be, but this is one where we should lay out that sample space again. I might do it in typing fashion, but I will order it a little bit better. The first thing I'm going to put in this table, the way that they kind of did a table as well, was basically the number of contestants who win and let's see how to say it. Probably exactly 2 of the 5 contestants win a prize during a week. Okay, it's 1 contestant a day, I guess. So what you have to look at is... Okay, never mind. I was going to do this a different way. Okay, let's just consider the sample space like this. I'll say that a W is going to represent a win, and L is going to represent a loss, as in not win. So with these things, the sample space, I'm going to choose them. I'm going to arrange them in all the different contestants that go. So you can either have all contestants win, 1, 2, 3, 4, 5, or have 4 win and 1 lose, or have, but I'm like, there are different ways you can have 4 win and 1 lose. So I guess that's what I want to say is basically, sorry about this. I'm trying to think about how to arrange this specifically. I want to have none win, 1 win, 2 win, 3 win, 4 win, 5 win. There we go. That's how I wanted to do it. I was trying to think if I needed to do the days or the number of wins, and it looks like I need to do number of wins. So let's do it that way. No wins means it will look like this. Every day they lose. In 1 win, there are a lot of ways you can do this. Either the last one can win, or the 4th one can win, or the 3rd one, or the 2nd one, or the 1st one. Those are the 5 different ways you can arrange 1 person winning. Now, with these other ones, this might take a while to spell out, so let me go from the bottom and kind of change this thing. The way that 5 people can win is just one way, like that, if they all win. Otherwise, you can have 4 win with a loss. You can have, this is going to be right next to each other, like this. Just basically the exact opposite of what you just saw on that side. Now, 2 and 3 in the middle is where you're going to get a lot more variation in what there is. And I might have to type this one out smaller, so I'm going to kind of shrink this up. So you can either have the last 2 win. This is going to be kind of hard for me to spell out. Or like that. I'm basically going to shift 1 over while this guy just kind of keeps winning at the end. because I can't think of other ways to do this fast, unfortunately. Now I got to shift them all up one. Let's see. Now I got to shift them all up one like this. Let's do this on the next thing. Shift them all up one like that. This is 2 wins. This is where I want to have ChatGPT say switch the letters for me, and I might pause the video for that, or I'll do it live and say, hey, this is how it worked. And whoops, I'm not supposed to shift him up yet. I'm gonna keep him on the backside. Win, loss, loss, win, loss, like that. Or I can do it like shift them up now. Or it can look like this. Okay, I think those are all the different ways that you can have 2 people win. I was just shifting it each time, so notice this W. I kept this W at the end while I shifted them over 1, 1, and 1, and then I shifted that W up 1 while this guy has to win over here, and boom, boom, and then shifted up 1 again, and shifted up 1 like that. Now, the 3 is going to be the exact opposite of these, meaning this is where I can go to ChatGPT or something like that and just say, reverse the W's and L's in here. Hold on, I'm going to do this live. You won't see it, but I'm just going to type this right now. Reverse the letters in my arrangement. Let's see if they actually just changed without me saying L and W or anything. Okay, I think it did it. So I'm going to copy and paste this. The reverse arrangement is this. Let's see if that works. Wait, what? Reverse becomes, oh, no. Hold on. They didn't do it right. I should be paused on this. Switch all W's and L's. Let's see if he does that. Okay, I think this worked. Okay, let's see if this worked here. So when I copy and paste, oh, it's all as one line now. But anyway, that's what showed up. So let me try it on here instead. Okay, when I copy and paste this, did that show up right? It did probably, but it's not tabbed over the same way. Okay, so I think that switched over that way. Anyway, I'm still on this problem as I talk about all this, and we still got to answer the question. But this is all the different ways that you can arrange this. Now, that might have seemed like a lot of work, and it kind of was. There are formula things for which we can break this down later and talk about it, but this is the way that we probably want to begin the conversation. And this conversation is, it says, what is the probability exactly 2 of the 5 contestants win a prize during a week? We had to arrange the number of different ways, and maybe you understood there was symmetry of this thing, but the different ways that 2 can arrange it out of how many different ways there are in total. So number of ways, there's 1 way for this, 1, 2, 3, 4, 5 here, 10 here, and you might, later when we talk about this, we'll see how this thing works, 10 and 5 and 1. But it's like that, so as a total, there's 1 plus 5 plus 10 doubled, so 16 doubled is 32, and there are 10 different ways that you can arrange for that. So the probability here is 10 out of 32. Now 10 out of 32 reduces to 5 out of 16, which is some value. Let's use the calculator for that. So 5 out of 16, I'll just go straight to the percentage. That's 0.3125, so 31.25%. So there's that. I should say a probability of two wins. So it's like that. So that's the answer to that, and that's the arrangement for it. And it takes quite a bit to get there when it comes to that. And like I said, there are formulas for this stuff, but it helps by understanding why this works the way it does to begin with. And I know that it took me a while to arrange that stuff, but it's going to take you the same way. And that's what we got. All right, let's go to number 8. On number 8, we have... I lost the thing now that I popped up my calculator in ChatGPT. All right, problem number 8. Your friend has 2 standard decks of 52 playing cards and asks you to randomly draw 1 card from each deck. What's the probability you will draw 2 spades? I hope I don't have to do 52 different arrangements. They did say spades, so maybe I can do the different suits. Okay, they all start with different letters. So there are diamonds, there are clubs, there are hearts, and there are spades. And I want to tell you this from the jump. I kind of probably... implied it in the beginning, but you are going to be doing coin flips, dice rolls, and card draws quite a bit. You probably understand the dice roll is 1 through 6 and the coin flip is heads and tails, but you're going to have to know things about cards as well. You're going to have to know that there are 4 suits in a deck. There are, 52 cards in a deck, 4 different suits. You're going to have to know their names, 2 different colors, red and black, that there are face cards, Jack, Queen, and King, and then the ace is something, Joker's wild, 2 through 9 is the number, or 2 through 10 actually, as the numbers. Actually, is there 10? No, I don't remember. Anyway, so with all that said, you're going to have to know certain things about cards with that. I don't think there's a 10. You're going to have to know certain things about cards within that set as you're rolling through. And actually, I think there's a 10. There's a 10. Okay, anyway. So diamonds, clubs, hearts, and spades are the ones here. Your friend has 2 standard decks. So there's a deck, and there's a deck when it comes to suit choice. So what's the probability you will draw 2 spades? Understand first what kind of sample space we have. It's possible, and I'm going to type this one out, it's possible that when you select them, you have, and I think this is the last time I'll be doing like these ones if we understand what the sample space is, but there's diamond, diamond, there's diamond club, there's diamond heart, and there's diamond spade of your 2 draws, or there's club, diamond, club, 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 heart, and club, spade. And understand that it's not about replacing the cards from the deck. They all have equal likelihood since they are 2 separate decks that this happens. There's heart, diamond, heart, club, heart, heart, and heart, spade. And there's spade, diamond, spade, club, spade, heart, and spade, spade. There are 16 different possibilities here because originally there were 4 sets to choose from the first deck with equal likelihood, 4 different sets to choose from the second deck with equal likelihood. So 16 outcomes. That wasn't the question, though. The question was, what's the probability that you will get a spade and another spade, 2 spades? There's only one thing here that has 2 spades. So that probability of 2 spades is 1 out of the 16. That's the desired or favorable out of the number of outcomes. That's number 8. Oh, I probably need a percentage. 1 divided by 16. There are times I'm going to forget to do the percentage. So it says 0.625. That's 6.25%. 6.25%. All right, let's go to number 9. Problem solving. You roll 2 6-sided dice. Find the probability that the sum is not 4 and the sum is greater than 5. So this is a case where I think listing out the sample space probably is better. I think for the sake of time and such, let me go back. Let me go back to this thing that we had here and just have it drawn out because, I mean, this is universal for any time you roll 2 dice. It's not like it changes per problem, so you might as well just have it handy. I'm sure if they had a card one, then I'd love to kind of do that card one at the same time, doing that. And yeah, anyway. So with this here, we're going to have this set. And there are 2 parts. There's a part A and a part B. So with this one copied down, we can refer to it. You could write them out, but there are 36 of them. So for part A, probability of sum is not 4. Sum not 4. Let's instead do 1 minus the probability that the sum is 4. Because there are less things with a sum of 4 than there are things with a sum of not 4. What is a sum of 4? 2 and 2, 1 and 3, 3 and 1. No other sets of dice rolls, a pair of dice rolls, will add to 4 except those ones. There is no 0 and there is no negative. There are no decimals. So this probability is 3 out of 36. Excuse me. Just the sum of 4 is 3 out of 36. So 1 minus 3 out of 36, which is 33 out of 36. Now, oh, I didn't notice I was choosing a new color. 33 out of 36 is divided by 3, that's 11 out of 12. 11/12ths chance, and of course, when it comes to percentage, it is 0.9166, so about 91.67% chance that it's not 4 as a sum. I wouldn't be a betting man on getting 4. I'd be a betting man on getting not 4 in that case. Of course, whenever I play Settlers of Catan, I seem to never get what I want in those situations. Part B. The sum is greater than 5. Probability that the sum is greater than 5 I think this is also better to use the complement version. Take 1 minus the probability that the sum is less than or equal to 5. I think there are less of those to count out, so let's go ahead and take a look at that one. Where's the sum less than or equal to 5? You see that this sum here is 2, 3, 4, and 5. So right here, that sum is 6. This sum is 5. Count that one. That sum is 6. This sum is 5. Count that one. And down here. So everything within here is where the sum is 5 or less. And this is everything else. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways that you can get a sum of 5 or less. That means there are everything else different ways that you can get a sum of more than 5. Not 5 or more, but more than 5. So this is 1 minus 10 out of 36, which is 26 out of 36. 26 out of 36 just divides by 2, and you can reduce that to 13 out of 18 as a fraction. And as a percentage, when we divide those, we get 0.7222. So 72.222%, repeating, of course, percent odds being greater than 5. All right, let's jump to number 10 with a part A-B. Problem solving. The age distribution of a population is shown. Find the probability of each event. Okay, this one might go a little faster because they have the split with numbers, and we'll just use percentages this time, no fractions. A person chosen at random is at least 15 years old. At least 15 years old means 15 years old or more. So you have two options. You can either take everything that's 15 years old or more, or take away everything that's not 15 years old or more. So I'd rather do the other way, because under 5 years old is here and 5 to 14 is here. Everything else is 15 years old or more. So let's just look at this set here where you have 7 plus 13, and we take that away from the 100%. This time, so probability of, how do they say it? A person chosen is at least 15 years old. So greater than or equal to 15. That'll be 1 minus the probability that we are less than 15 years old for age. I'm just putting X as age. Which is 1 minus, and that's the sum of these two guys here. 7%, excuse me, I'll say 100. I'll say 100 in this case. 100% minus 7 plus 13. Should we write them as fractions? Now I'm thinking about them. When they have percentages, I'm thinking maybe I should do fractions instead and just say it that way. I won't, because they have as percentages. Anyway, please understand I just went to percentages now, even though I put probability. So that's 100 minus 20, which is 80%. 80% chance that a person chosen at random is like that, theoretically. That's part A. Part B. I've already gone like an hour. I'm sorry. I didn't say this would be quick. I thought it would be quicker than this. Other stats sections should be faster once we do things with formula things, unless I have a lot to explain. This had a lot to write out, and I had a lot of ways to cope with it, and you had to go through them. Part B, a person chosen at random is from 25 to 44 years old. So let's find that. 25 to 34 is in this one right there, and it goes all the way 35 to 44. Let's just add those two up instead of doing a complement version. So probability that X is between and including 25 and 44. That's going to be 13% plus 13%, which is 26%. Remember, 26% is also 0.26. It's 26 out of 100. If you do fractions like that, you can write it that way. I'm going to stick with the percentages as long as they're written as percentages. All right, numbers 11 and 12, it looks like, are error analysis. Let's look at the first one and see what we want to correct. A student randomly guesses the answers to 2 true-false questions. Describe and correct the error in finding the probability of the student guessing both answers correctly. A student can either guess 2 incorrect answers, 2 correct answers, or 1 of each, so the probability of guessing both is 1/3. So the issue with this is assuming that whether you get the first correct and the second incorrect, or the first correct and the second incorrect, I forget if I just said the same thing twice, but swapping them are treated as the same thing, and they shouldn't. They shouldn't. When it comes to overall weighting, there are more ways that you can get one question correct than getting both correct versus both incorrect. Our sample space should be, and I'm going to write them out first, you can either get both incorrect or the second one correct, or the first one correct, or both correct. But that's 4 different total outcomes. Even though getting both correct is 1 out of something, it's not 1 out of 3. These are 2 different ways. 2 diff ways. So the correcting this, they never accounted for the fact that there are 2 different ways to get a problem correct and another problem incorrect. So exactly 1 problem correct, basically. That needs to favor in the weighting. That balances it out. That's why it's more likely that that can happen, getting just 1 correct, exactly 1 correct there. So the probability here is, I'll just put P equals 1/4 for the both correct. I guess that's what I want to write. Probability of both correct equals 1 out of 4. Not 1 out of 3. Okay, number 12. A student randomly draws a number between 1 and 30. Describe and correct the error in finding the probability that the number drawn is greater than 4. Excuse me. The probability a number drawn is less than 4 is 3 out of 30. Or, less than, yes. Or 1 out of 10. So probability numbers greater than 4 is 1 out of 10, or 9/10. Let's see. Yeah, no. What they wrote was kind of incorrect here because we never counted that a student draws a 4. So they are trying to find, they're doing the complement idea right, they just kind of messed up on it. They are trying to find a number greater than 4, so they are seeking all numbers not greater than 4, but they forgot about 4 itself when stating 3 out of 30 probability. See, the thing is, they said the probability the number is less than 4. We don't want to do less than 4. We want to say less than or equal to 4. So probability that a number is greater than 4 is 1 minus the probability that the number is not less than 4, but less than or equal to 4. 4 matters in that case. So 1 minus 4 out of 30. Now, I'm reducing the fraction last, not first like they did. 26, it doesn't matter. And that's 13 out of 15, and that's how we're going to write that. They didn't write anything after that when it comes to decimal, so I'll just leave it like that as a fraction as well. But 13 out of 15 odds, which is less than 9 out of 10. All right, let's go to number 13. So, number 13, you roll a 6-sided die 60 times. Sounds like an experimental probability. For which number, the table shows the results. For which number is the experimental probability of rolling the number the same as the theoretical probability? So when you roll a 6-sided die, we want to understand that the probability of theoretically, the probability of landing of any of these is the same. You get 1 out of 6 chance for any of them. We want to figure out which one through experimentation also is 1 out of 6, or what divided by 60 does give you 1/6. So experimentally speaking, the probability of rolling a 1 was 11 out of 60. Now that does not land on 1/60th. The probability of 2 is 14 out of 60. It does reduce, but just to 7 out of 30. That's also not 1 out of 60. The probability of 3 is 7 out of 60, which does not reduce, and also therefore is not 1 out of 6. Sorry if I was saying 1 out of 60. I meant 1 out of 6. Sorry about that. Number 4, probability of 4 is 10 out of 60, and that reduces to 1/6, and that's the one that we're looking for. Now, is there another one that has it? We got to check. So anything that has 10, basically, right? Obviously, I'm probably over extrapolating there, but 6 out of 60 is 1/10, also not it. And then the last one, 12 out of 60, is 1/5. So none of those, it looks like just the 4 is the same of them. So for which number is the probability the same as the experimental, the same as the theoretical? That one. Number 14, a bag contains 5 marbles that are each a different color: white, black, red, green, blue. A marble is drawn, its color is recorded, and the marble is placed back in the bag. This process, so that's important so that we know that you get equal probability there. And like they shuffle it up afterward too. So the one that you place in is equally likely to draw again than any other one that's in there. This process is repeated 30 times until, theoretically, until marbles have been drawn. Until 30 marbles have been drawn, table shows the results. Which probability is experimental? Same as the theoretical. So, I mean, at this point, I think it's just important for us to talk about the idea, 5 marbles each a different color. They're all equally likely to be drawn. So we're looking for which one has probability of which one gets us 1/5. I know I didn't write that last time. Probably should have. So probability of which one would have given us 1/6 because that was in theory. And so which one would give us 1/5? Which one is something divided by 30? So listen, I'm going to do this a different way this time. What divided by 30 is the same as 1/5? If you multiply both sides by 30, we're taking 1/5 of 30 to get 6. Which one gives you 6? Which one gives you 6? It looks like it's black. Black gives you 6. So probability of black is, I should say BLA because there's blue. I should write black. I'm writing in black. Does that count? Probability of black is 6 out of 30, which is 1/5. That's the one that works, so it is black. Did I have to show that part right there? Probably not. But black is the answer. Yeah, I mean, I don't know which way I'm required to do the problem, but that's the way I would do it a little bit more so. Say which one gives me the same fraction instead of testing them all out until I get it right. Okay, number 15. Refer to the spinner shown. The spinner is divided into sections with the same area. Kind of like a clock, only it's divided into tenths. So 10% chance of anything happening, right? 1/10. Okay, let's see. What is the theoretical probability that the spinner stops on a multiple of 3? Part A. All right, so multiple of 3. What are some numbers that are 3? So this is where I might want to work on sample space stuff. So multiple of 3 are the following numbers here. 6, 9, 12, 15, 18. So pretty much everything but 4. 21, 24, 27, 30. Everything but 4. So the probability of, did it say probability? That stops on a multiple of 3. We have one of two options. We can either count how many we did, which I guess is 9. So 9 out of 10, and I'll just write that as 90%. That's part A. Or we could have subtracted the 10% away where the 4 was. But there's part A. Part B. You spin the spinner 30 times, experimental. It stops on a multiple of 3 20 times. What is the experimental probability of stopping on a multiple of 3? Well, we spun it 30 times experimentally, so same thing, probability multiple of 3, but this time it's 20 out of 30, which reduces to 2/3. If you equate it to the 9/10, it would be, I guess you can't divide it by 3 to say, 6.6 repeating out of 10. Yeah, because 2/3 is about 66.67%, right? 2/3. Anyway, it's a lesser probability, basically. Experimentally so. Experimentally so. That must mean we hit 4. You hit 4 10 times in that set. That's very unlikely. And that's something that you can talk about in the future. Explain why the probability found in part B is different than the probability found in part A. Because it's rigged. It's a rigged system. Because in experimentation, anything is possible. In experimentation, the trials do not necessarily always match the favorable outcomes. Right? If I flip a coin 100 times, there's a chance that I do not ever land on heads. Theoretically, I should land on it 50% of the time or roundabouts, right? Experimentally so, it's probably going to happen. Landing on 0 out of 100, I'll say that is a statistical impossibility without stating it's a statistical impossibility. But you have to include it in your sample space of being possible. Just like it's possible of anything else, but it's less likely because there's only one scenario that happens out of the quadrillions of different ways you can do it. Probably even more than that. Oh, there's a part D. Part D. You spin the spinner 60 times. It stops on a multiple of 10 6 times. How does the experimental probability of stopping on a multiple of 10 compare to the theoretical probability? So let's find the multiples of 10. So multiples of 10 include just 30. I didn't see that. So probability multiple of 10 equals 1 out of 10. They said it landed on a multiple of 10 6 times. So that's theoretical. And let's go to experimental probability. That's 6. Multiple of 10 6 times. 6 out of 60. That's also 1/10 when reduced. These are the same. So they say, how do they compare? They are the same. They are the same. Will that always happen? No. Obviously, we just saw things where they didn't happen. They're making up the numbers. But it came out as expected. We experimented as expected. All right, number 16, open-ended. We're about halfway done. Describe a real-life event that has a probability of 0, then describe a real-life event that has a probability of 1. Me ever being able to date Lindsay Lohan as a probability of 0, right? So that, I mean, I think they want mathematical kinds of, or things that we're talking about, rolling a die, flipping a coin, things like that. So let's just talk about it like that, right? What's an absolute certainty? What's an absolute impossibility? So I'll be very generic with this. Rolling a die. So hold on. Okay, rolling. Let's see. Real life event probability of 0. That's 0%. 0% certainty. Rolling a die and landing on a number greater than 6. A standard die. Standard die that goes 1 through 6. It's just 0% chance. That's a weird way to spell probability. Where's the I? There it is. All right. Probability of 1. Sorry, I have a microphone in my probability. Why does that keep happening? I know I'm typing the I. Probability of 1. Rolling a standard die and landing on a number between 0 and 6. Oh, 1 and 6. Between 1 and 6. It's always going to happen. So that's, yeah, it was open-ended. I just made that one up. Okay, anyway, let's keep moving. Number 17. Drawing conclusions. A survey of 2,237 adults aged 18 and over asked which sport is their favorite. Come on, man. Be better. Auto racing? Where did they... Oh, they did this in the South. The results are shown in the figure. What is the probability an adult chosen at random prefers auto racing? So I'm going to assume, so like in the lecture portion, they were talking about something about pet owners and stuff, but it looks like this number should actually add up to 2237. So when we're looking at these numbers in this bar graph, if you will, auto racing comes up 179 times out of the 2237. Auto racing. That equals 179 out of 2237. And that's about, let's see, 179. 0.0, here, I'm first write the decimal, 0.08001, and it kind of does 8 and some other stuff. It does a 7, but I'm just rounding up. So from there, that's around 8%. 8%. Because 8.00%, I mean, 8% probability. All right, that was a fast one. Looks like we're speeding up as we go. That is not generally the case in problem sets. Number 18, drawing conclusions. A survey of 2,392 adults ages 18 and over asked what type of food they would most likely to choose at a restaurant. Where's steak? Oh. The results are shown in the figure. What's the probability an adult chosen at random prefers Italian food? So once again, this should total to 2,392. Italian is in pink. I do apologize for the colorblind crowd out there. I'm being legit serious. I want to point to the fact that this is right there, because who knows when it comes to not being able to tell certain things that bleed over. So that is Italian. So for number 18, probability of Italian, it should be high, and it is high. 526 out of 2,392, which is about, excuse me, decimal first, 0.2199. It's around 22%, but I'm going to say 21.99% because I don't know what kind of answer they want when it comes to rounding. Around 22%, though. In exercises 19 to 22, use the spinner in exercises 15 to find the given odds. Notice they did say the word odds now and not probability. So odds means we have to, wait, where's 15? Oh, I have to go back. Let me copy and paste what 15 was. What was it? Oh, the spinner. So let me copy and paste this spinner because I'm going to be on the other page. Odds is not probability. Odds is favorable outcomes divided by not total, but unfavorable outcomes. Basically everything that's not your thing. I'll write it out kind of as a formula the first time through, and after that, hopefully we can work it out. So number 19, the odds in favor of stopping on a multiple of 6. First of all, let's just think about probability of stopping on a multiple of 6 first. So stopping on a multiple of 6 is here, 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 and here. You have multiple of 6 by probability standards is 5 out of 10, right? However, the odds, I'm going to put an O here, odds on multiple of 6, you have 5 outcomes for which you can land on 6. You have 5 outcomes for which you would not land on 6. So that's 5 to 5 odds, right? Really means 1 to 1. 5 to 5 odds means 1 to 1. You have not 1%. You are equally likely to land on a 6 as you are to not land on a 6. And that's what that idea is. I shouldn't write it as a fraction. I should write it as its ratio counterpart. So 1 to 1. 1 in landing on 6, 1 in not landing on 6. Equally likely. That's where the 50-50 comes from, right? 50%. Number 20. Number 20, we have in favor of stopping on a number greater than 10. This is odds. So odds in favor of stopping on a number greater than 10. It looks like this thing ascends. So where does the greater than 10 start? It starts there and it goes up. I can either count those or I can count away from it. So 4, 6, and 9. So the odds of greater than 10. Sorry if that, I'm just saying it out loud. So hopefully that helps. Odds of greater than 10. This is going to be 1 minus. Oh, maybe I shouldn't do the 1 minus. Okay, anyway, there are 7 numbers that are greater than 10 here. So 7 versus, oh, I should just write this anyway. 7 versus 3 that are not. 7 to 3 odds. 7 to 3 odds. Okay, number 21. Odds against stopping on a number less than 9. So against stopping on a number less than 9 are for stopping on a number greater than or equal to 9. So here are the numbers that are less than 9, right? So we got to think of what the 4 is in this case. Or when we say that, yeah, we still want to look at the against itself. What are the odds against it? So odds, against, I don't know how to write this format best. I feel like I shouldn't copy anything down. Against less than 9. So odds against less than 9, again, they're not for, oh yeah, I guess they're not for less than 9, they are against it. So odds against less than 9 is like the 1 minus 4. So odds for greater than or equal to 9 is kind of the way that I want to put that. So what are the odds for greater than or equal to 9? Here's the 4. That's 8 to 2. 8 to 2. Sorry for me kind of saying this in kind of a weirdish way, which reduces to 4 to 1. If you want to write it as a fraction first, you can, but we can also write the ratio and just do the division that way. You know why I stumble upon these? Because I'm very rusty on them. I am. Listen, admittedly, I'm very rusty on this kind of stuff. It's not stuff that I actually do. I teach algebra, I teach geometry stuff. I don't do many statistic things. So for me to go back to them, I have to talk through it and think through it logically. And honestly, that's kind of what I like about these, because these have very real world implications that we've talked probability and odds without computing these. And we understand arrangements of these that I think we can figure them out. You can work them out through conversation. And it's okay to not get a one-shot answer immediately. Not everything needs a formula. Odds against stopping on a number that's divisible by 7. Let's find the ones that are divisible by 7, because I think there are fewer than the ones that are not. So divisible by 7, we have 1. I think just 1. So odds against it. Odds against means everything else that's not the 7. So odds against it. Odds against divisible by 7 is, there's 1. So 9 to 1. 9 to 1 odds. Against it, right? Not for it. 4 would be 1 to 9, and this one's 9 to 1. So you basically just reverse it. You just reverse what's there. Okay, let's keep moving forward. Let's look at number 23 and 24 on problem solving. Number 23, the odds of winning a lottery game are 3 to 5. The probability of winning a bingo game is 35%. Which game gives you a better chance of winning? Explain. So the probability of the lottery game is not 3 over 5. It's 3 over 3 plus 5. Because the 3 to 5 odds means 3, 4, and 5 against. That's 3, 4, and 8 total. So 3 out of 8. And 3 out of 8, we already saw this number. This was 37.5%. So 37.5% here. Whereas the probability, they do say probability here, of bingo is 35%. So the question is, which games gives you a better chance of winning? The lottery one. My explanation is my math, but based on the math there, lottery is a better chance of winning. Not by much, but take better odds when you can get them. Number 24, maybe I can fit it down here. Probability of winning a carnival game is 1 to 4, whereas the odds of winning a raffle are 1 to 3. For which do you have a better chance of winning? Explain. So the carnival probability is spelled out. That is 1 out of 4. We'll just leave it as a fraction. Probability of the raffle is, it's 1 to 3 odds. That means 1, 4, 3 against. That's 1. That's 4 total. So 1/4 and 1/4. You have equal likelihood. Equal likelihood. That 1 to 3 means 1 out of 4 there. Okay. Number 25, reasoning. Use the spinner in exercise 15. Oh, do I still have it copied? Yes, I do. To give an example of an event whose odds are 1 to 1. I think we had one. We had one, but we have to probably make up another one. This is kind of open-ended here. So what's something that I can select that's exactly divided? Last time it was what? Multiples of 6? Let's do multiple. You know, instead of doing multiples, let's just divide it here because it increases in size, right? So let's divide it right down the split down the middle, and let's do anything that's less than or equal to 15, or less than whatever. So use to give an example of an event whose odds are 1 to 1. The odds. Whoa. How about? Let's do that again. The odds of landing on a number less than or equal to 15. That would give you 5 to 5 odds, either 5 here to 5 there, which is also 1 to 1. 1 to 1 odds. Example. Okay, number 26. Analyzing relationships. Refer to the chart below and answer parts A and B. And part A has 4 parts. That's good. Oh, those aren't 4 parts. That's an arrangement. So Friday, 5% chance of rain. Saturday, 30%. Sunday, 80%. Monday, 90%. Reminds me of some of the spring when it came to softball and canceling things. Order the following events from least likely to most likely. A, it rains on Sunday. B, it does not rain on Saturday. C, it rains on Monday. D, it does not rain on Friday. Let's first come up with what those events from least to let's arrange those probabilities first. So probability of rain Sunday is 80%. Probability of not rain Saturday. I don't know. Should I put Saturday with a hat? Sat hat? Sat hat is, and I haven't been doing that. I apologize for not having done that a little bit. I've been saying not each time. But sat hat is 1 minus the probability of Saturday's rain. So 100% minus 30%, which is 70%. That's less likely than Sunday's rain. Probability of Monday's rain is 90%. And probability of Fryhat not rain on Friday is 100 minus 5, which is 95%. So 95% chance it does not rain on Friday, which is more likely than any other outcome we have. So as far as things here, they have the letters, so I'm just going to arrange them that way. This was A, B, C, and D. So from least likely to most likely, least likely is B, that it will not rain on Saturday, and then A, that it will rain on Sunday, and then C, it will rain on Monday, and D, it will not rain on Friday. It is most likely among all these that it will not rain on Friday. Cool. Part B, I was about to say number 27, but we're not there yet. Part B, find the odds in favor of rain for each day. So the odds are basically the thing minus it not happening. So for Friday, does not rain, keep in mind that it's the opposite of what you have. So that's 95 to 5 odds. Because for not rain, 95 to 5 odds. If you divide those by 5, you get 19 to 1. You get 19 to 1 odds it will not rain on Friday. Saturday, not raining Saturday is 70% chance. That's 70 to 30 odds, which is also 7 to 3 odds. I hope I'm kind of saying these right. Sunday, not raining Sunday is 20% chance. That's 20 in favor of not raining versus 80 in favor of raining, which reduces, if you divide it by 20, 1 to 4 odds. And then Monday, not raining is a 10% chance to the 90% chance of raining. Divide those by 10 and you get 1 to 9 odds for those ones. So assuming that we're just trying to reduce in those situations, that's what we'd say for all of those different sets as we kind of talk through them. You know, if that makes sense. Okay. So those are in favor of, it says of rain. Why did I thought it said not rain? I don't know why it said that. Sorry, let's switch everything up. Oh my goodness, I'm so sorry. At least it'll go super fast. Let me just pause that and change it. Sorry about that. I think that probably happened. I think I saw the one that says not rain on Friday. And then I think I saw that. And then I kept going from there. I should have scrolled down a little bit more. Okay, yeah, at least this latter half is going faster, either because we understand it more or we don't have to list all those samples and things. So about 6 questions left. Number 27. Probably no proofs or graphs, which is good. Use the figure in example 3 to answer each question. I gotta find example 3. I think it's the dice thing, so we used that last time. Give me a second. Okay, so I went back and it was indeed example 3, so I just copied it. I'm pasting it in. So, use example to answer each question. List the possible sums that result from rolling 2 6-sided dice. Does that mean just like... the sums. I thought they said something else. I thought they said the sums that add to 6. So, the possible sums... Now, in this case, we're not talking about repeats. So even though you can land on 6 by doing 3 and 3, 2 and 4, and 1 and 5, and 5 and 1, stuff like that, it doesn't matter. In this case, just the different possible sums that there are. So you can either get snake eyes, 1 plus 1 and get 2, 1 plus 2 and get 3, 1 plus 3 and get 4, 1 plus 4 and get 5, 1 plus 5 and get 6, 1 plus 6 and get 7. Now you might, hey, 3 plus 4 is 7. Yeah, I know. I'm just saying that these are possible sums you can get from 1. There is no 1 plus 7, so you can do 2 plus 6, 3 plus 6, 4 plus 6, 5 plus 6, and 6 plus 6. Let me get that in there. 12. Again, I'm not saying those are the only ways you can get them. I'm saying these are possible to get. These are sums that are possible from any which way. So those are the possible sums. I guess that is part A. So, boom. Part B, find the theoretical probability of rolling each sum. This is where it kind of changes, and this time we have the list. So what I kind of saw last time and liked, and I think I've seen this stuff before, the 2, notice that the 2 can only be rolled from the snake eyes. So this is the frequency I'm going to show you here. A 3 you can get from 1 and 2 or 2 and 1. So that's 2 different ways. The 4 you can get from 1, 3, 2, 2, or 3, 1. And that's 3 different ways. And then 4 different ways to get, sorry, that was 4. 4 different ways to get 5. And then, sorry, I'm leaking over on some of these here. 5 different ways to get 6. Getting 7 is right here. So it's really cool how it goes across. And you're going to notice symmetry going the rest of the way here. So 6 different ways to get 7. And then it goes back down. For 8, there are 5 different ways again. And I think from there you can start to get the hint at what's going to happen after 4, 3, 2, 1. 1 being the 12 by 12. And you can see where that kind of falls in line. So just through those diagonals, and that's why I like the visual, through those diagonals you can kind of see that frequency set. So what did they say? Find the theoretical probability of rolling each sum. Now that we say the frequency, and out of 36 of them, the probability of getting a sum of 2 is 1 out of 36. Probability of 3 is 2 out of 36, or 1 out of 18. I'm going to leave them as fractions, by the way. Probability of 4 is 3 out of 36, or 1 out of 12. Probability of 5 is 4 out of 36, or 1 out of 9. Probability sum of 6 is 5 out of 36. That can't reduce. Probability of 7, most likely, is 6 out of 36, or 1/6. Now, as you do the others, it'll just go kind of back down the other way. So probability of 8, back to 5 out of 36. Probability of 9 is the 4 out of 36. That's your 1/9. So I'll just write that. Probability of 10 is the 1/12. And then 1/18 and 1 out of 36 for the rest of them. Okay, those are the different probabilities of those. Part C. And I probably need to leave these up because they're saying experimental or simulation. Part C. The table below shows a simulation of rolling 2 6-sided dice 3 times. Use a random number generator to simulate rolling 2 6-sided dice 50 times. Compare the experimental probabilities of rolling each sum with the theoretical probabilities. Oh, so I need to do this. I'll ask ChatGPT to do it. So I'll use this same thread as before. Use a random number generator to simulate. So I'll say simulate rolling 2 6-sided dice 50 times. Display the numbers. Let's see. Display the numbers in 2 separate columns. All right, let's see what they say. So they say the roll number. So it shows a roll number and then the die from them, die 1 and die 2, and it's going to do this here. I won't be able to display this. Well, hold on. Maybe I can find a way to display this thing for you. Give me 1 second. I don't know if I can. Let me try something because it's still spitting them out. It's getting a second here. Do I have to use studio mode? Give me 1 moment. Google Chrome, ChatGPT window. Okay, this might work. So I'm going to switch over to something. I don't know how to do this. Transition. Okay, I'll figure it out. Right here, Google Chrome. That work? Okay, here we go. So in ChatGPT, here's a simulation of rolling 2 6-sided die 50 times. So here's die 1 and die 2, etc. And it's showing all of those there. This is the roll number. So 50 rolls and it shows all that. Perfect. Okay, so there's that. I don't know what they wanted to do with it. Compare the experimental probabilities of rolling each sum with the theoretical probabilities. Oh, I didn't calculate the sums. Can you display a third column? Oh, you know what? I can do the sums myself, but you just won't be able to see them. So I'll have to do something with that. I have to do this in a spreadsheet. Sorry about this, but yeah, that's what you can do. Unfortunately, I don't know if I can display this, but I'm going to... Oh, I could. I can just do Google Drive. I don't need to do Excel. Or Google Sheets, I should say. So let me go back to what I was talking about. I'm going to my Chrome browser. All right, so here I'm copying and pasting what he did here. ChatGPT is a he. Roll number, die 1, die 2, and let's get the total. So we're going to get the sum of those. There are probably calculator things on. They're like website things that do this. But here are our different sums, okay? So this bold one are going to be the different sums. Now what they want is compare the experimental probabilities of rolling each sum with the theoretical probabilities. So let's see if I can do that. I want to say count if this number is a 2. This number is a 2. And I want to do that same thing for, it only landed on 2 once. 1 out of 50 times instead of the 1. I guess that makes sense. 1 out of 36 was the theoretical probability. I guess that's the most likely outcome for that to happen. It was only going to land once or twice. That makes a whole lot of sense. Let me make sure that this locks onto those sets here. And we're going to do the same thing for, actually, let's put this here. Let's copy that and paste that here. I'm going to put instead, not 2, but this value right there. That's A3. Sorry about this. I'm just going to kind of code this thing in. So the next ones are going to be for 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's these numbers here. So this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, sorry. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so roll sum and like the value and then the frequency, okay? So let's compare these. So check this out. As it spreads out, it was most about 6 got the most instead of 7, but you see that spread trend upwards and back downwards through the experiment. So the probabilities, let's see, experimental probability and theoretical probability. So theoretical probability was going to be what? 1 out of 36, 2 out of 36, 3 out of 36, 4, 6 out of 36, and then back 5, 4, 3, 2, and 1. So there were, whoops, did I do cut and paste? My bad. 2 and 1. Okay, those are the theoreticals. Let's reduce those decimal counts to that. In fact, let's see them as percentages. Percentage. And then the experimental. Let's do this divided by 36. Wait, out of 50. Out of 50, right? And then copy paste those ones and write those as percentages. Those are kind of exact numbers there. So maybe I should, yeah, whatever. Okay, so let's just compare them. I know we did a lot of things for this one part. I did not expect this at all. Give me a sec. I'm going to kind of copy and paste this part now. Okay, let's bring our set back. I'm going to copy and paste what I have here. Our experimental versus our theoretical from that set. So that's the comparison. They gave their own. I'm doing my own here. So how do they compare? They're pretty close to each other. I mean, as an overall, they have that upward trend. Obviously, clearly, this was higher than, that whatever, the experimental versus theoretical. But it matches up. And listen, if I grow that sum, ChatGPT did it for me. But if I did that 1,000 times, you would start seeing it lean closer and closer to this. It's just the nature of what happens. That's just how probabilities work. The larger the sample size, the more likely it trends toward that. All right, that was part C. I think that's the end of number 27. Let's move forward. Number 28, making an argument. You flip a coin 3 times. It lands on heads twice and on tails once. Your friend concludes the theoretical probability of the coin landing heads up is 2/3. Is your friend correct? Explain your reasoning. Your friend would be correct through experimental probability, but not theoretical probability. And that's kind of what I want to type exactly here. My friend would be correct if we were referring to experimental probability, but it's not theoretical probability. The theoretical of landing on heads is 1/2 or 50 or 0.5, 50%. Period. Okay, sorry. I was looking at the thing. I technically be 1.5 out of 3 because you're flipping it 3 times, theoretically speaking. Anyway, so here we go. All right, number 29. Critical thinking. You randomly draw a marble from a bag containing red, white, and blue marbles. The odds against drawing a white marble are 47-3. That means against are 47-3. That means for are 3-47. So probability for white. Excuse me. Oh yeah, let me just say probability. Probability for white is 3 out of 47 plus 3. 3 out of 50. There are less than 100 marbles in the bag. How many marbles are in the bag? Justify your answer. Keep in mind we probably need an integer amount for these odds to occur. So 100 needs to be a multiple, 100 is a multiple of 50, but if it's less than 100, you need to stay within multiples of 50 for this to work out. Otherwise, this cannot maintain integer status. And drawing a white needs to have integer kind of status number of times that it can be drawn. So for part A, there are less than 100 marbles in the bag. How many marbles in the bag? Justify your answer. There are 50. There are 50 marbles in the bag. We need a multiple of 50 to be represented, and the total outcomes, the probability of white weighs itself against 50 in total. That's because the odds, the 47-3 against white also means 3-47 for white. That means a total of 50. Part B. The probability of drawing a red marble is 0.5. 0.5, that's the same as, same as 1/2. And 1/2 is, in the case of, I don't know if this matters, but 25 out of 50. If just because that was, I want to weigh them evenly in case I have to use that. What is the probability of drawing a blue marble? Explain your reasoning. So if drawing a white marble is 3 out of 50 and drawing a red marble is 25 out of 50, the probability of blue is 1 minus the probability of white or red. So 3 plus 25, which is 1 minus 28, which is 22 out of 50. 22 out of 50. I don't know if we need to write that other number there, but that'd be 44%. 44% chance of drawing a blue marble. As red is 50%, we get 44 from that set there. Okay, let's go to number 30. How do you see it? Consider the graph of f shown. What is the probability that the graph of y equals f of x plus c intersects the x-axis when c is a randomly chosen integer from 1 to 6? Explain. So on the x-axis, we have 1, 2, 3, 4, 5, 6, and chosen at random, the probability it hits the axis among those, 1 out of 6. Oh, C is, never mind. Hold on. It didn't say that. It didn't say C is a number on the x-axis. It says C is a number from this constant here. That's a vertical translation value for C. So f of x is already established as this function. So from this function, you can either shift up or shift down, things like that. But they said if you're adding C and C is 1 to 6, here's where the vertex goes if C is 1. I'm not saying it has to hit the vertex, but I'm saying that the graph looks like that when C is 1. When C is 2, plus 2, it's right there. When C is 3, it's right here. And you can notice we're hitting the x-axis still on these. When C is 4, we hit the x-axis on the vertex. When C is 5, we don't hit it anymore, right? It's right there. And when C is 6, we also don't hit it up here. So we hit it on 4 out of the 6 times, or 2/3 of the times. I think that's what they're saying, because the f of x plus c shows that there. So what is the probability the graph there intersects the x-axis? Probability intersects x, whatever, is 4 out of 6, or 2/3, when c is any number between 1 and 6, because of that shift. I'm explaining it to you out loud with that based on the visual, and it's hitting the x-axis all the way up. Okay, number 31, drawing conclusions. A manufacturer tests 1,200 computers and finds 9 of them have defects. Find the probability chosen at random has a defect. Well, that's 9 out of 1,200. So probability of a defect is 9 out of 1,200, which reduces to 3 out of 400. I feel like a decimal is in order for that. So 3, or a percentage, 3 divided by 400 is 0.0075. That's 0.75%. Less than 1% chance of defect. That's good. I mean, that seems high still, but whatever. Predicts the number of computers with defects in a shipment of 15,000 computers. Explain your reasoning. Well, you could do a proportion. We could say if 3 out of every 400 are defective, then X out of every 15,000 are defective. We also know what that number is, 0.0075. I mean, at this point, I might as well just write it like this. So X is 3/400 times 15,000, and I should be able to compute that off the top of my head. I'll just let my calculator do it. 3 divided by 400 times 15,000, 112.5 defective. I don't know whether I'm supposed to round up or down from that. What do they say? Predict the number of computers with defects. 112 or 113. 112 or 113, somewhere in between. Maybe it's half defective. Maybe it's on its way toward being defective. Or you just say 112.5. I don't know. They should have given me a whole number. I don't know why they didn't. And I think it's the last question, number 32. The tree diagram shows a sample space. Write a probability problem that can be represented by the sample space, then write the answers to the problem. All right, well, so here's a tree diagram. Yeah, they have, so it's kind of open-ended, I guess. Box A, 1, 2, 3. Box B, 1, 2, 1, 2, 1, 2. So you have I guess there are numbers in a box. They said write a problem. So, okay. There are, box A contains the numbers 1, 2, and 3. Box B contains the numbers 1 and 2. So what's happening here in this tree diagram, it's showing a display of you can either choose 1, 2, or 3 from box A, and you can only choose 1 or 2 from box B. And then they're showing what happens if you choose 1 from box A, you can choose 1 or 2, and then those are the different outcomes. If you choose 2 from box A, there's 1. And they show them separated by commas, so it doesn't look like 11 and 12 and 21 and things like that. And they show their sums and their products. 1 times 1 is, or 1 plus 1 is 2, 1 times 1 is 1, and things like that. So there's the scenario. So how about this? If each number is equally likely to be chosen, and a number from each box is chosen at random, what is the probability? It said probability, right? Probability problem. What is the probability that, let's do sum, that the sum of the outcomes, the numbers in each box, is less than 4? Is less than 4. So when we look at the sums, the different things we have are 2, 3, 3, 4, 4, and 5. So probability of less than 4. There are 3 that are less than 4. There's the 2, 2, and 3, and there are 6 options total. So that's 1/2 or 50% of that one. 50% chance that when you select numbers at random from the boxes, that the sum of those two numbers will be less than 4 is 50%. All right, guys, and I think that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. I feel like this one was a little cluttered, and I'll probably clean up as I go with this because I haven't really talked about probability in a long time, because now that I've talked about it with you guys, you'll make more sense of it as well. And I think they're going to dive more into formula aspects that we can utilize. I feel like the back end of that was a lot better than how I was trying to work out the front end and say use chat GPT and whatever. And I know I swapped some things around. That's just my bad. My brain's cooked at times. It's the end of the year, so apologies for that. Anyway, thank you so much for watching. Take care, and I will see you in the next one.